In this lecture, we are going to look at applications of linear algebra to the study of fields. And we begin with the definition. Characteristic of a field F is the smallest natural number n such that 1 plus 1 plus 1 plus 1 n times is equal to 0 in F. If such a number does not exist, we say that F has characteristic 0. So let's look at an example. Let's take a field to be Z3. So in Z3, we know that 1 plus 1 plus 1, which is 3, is equal to 0 in Z3. So this tells us that characteristic of Z3 is equal to 3. So if we take F to be real numbers, then so here it doesn't matter how many ones we are going to add up. So this is never equal to 0. So this means that characteristic of the field of real numbers is equal to 0. So really, it would be more appropriate to say that instead of saying characteristic 0, it would be more appropriate to say characteristic infinity. However, the accepted terminology is characteristic 0. So we can generalize an example with Z3, and so if we take P to be a prime number, then we know that ZP is a field. And in this case, so characteristic of ZP is equal to P. Because if we add 1 with itself P times, then we're going to get 0. And this is the smallest number of ones that we need to add to get 0. So let us study the properties of a characteristic. So we begin with the following lemma. So let F be a finite field. So this means it's a field with finitely many elements. Then F has a non-zero characteristic. So in other words, so there is a finite number of ones that we add together, and we can get 0. So to prove this, so we consider a sequence of elements of F. So we start with 1, then we take 1 plus 1, then we take 1 plus 1 plus 1, and so on. So we just add 1 every time. And we consider an infinite sequence of this type. So since we have an infinite sequence, but the field is finite, so since f is finite, there will be repeating terms in this sequence. So this means that if we have 1 plus 1 plus 1 m times, so we can find numbers m and k such that the sum of m ones will be equal to a sum of k ones, where m is greater than k. But then, so what we can write this equality can be written as 1 plus 1 plus 1 k times plus 1 plus 1 m minus k times. And this is equal to 1 plus 1 plus 1 k times plus 0. But then in a field we had the following property, that if a plus b is equal to a plus c, then this implies that b is equal to c. Right? So we proved this cancellation law in a field. And then if we apply this property to this situation, then we get that 1 plus 1 plus 1 m minus k times is going to be 0, where m minus k is greater than 0, right? So here we made this assumption. And so this means that in any finite field, we can find the finite number of ones that we add together and we get 0. So this means that we can even find the smallest such a sum that makes 0, and this will be the characteristic of a field. And so we proved that for a finite field, the characteristic must be finite number. Next, let us show that characteristic of a field cannot be just any natural number. So here we have a lemma. So let f be a field of characteristic n, which is different from 0. Then n is a prime number. So let's prove this. So we're going to prove by contradiction. Suppose n is composite. So n is m times k, where m and k are both greater than 1. So then, if we write the sum of n ones, then, well, this is going to be 0 because it's a characteristic of a field. But because n is composite, so this sum can be factored as a product. So if we take m ones and multiply by the sum of k ones, right? So if we use the distributive law, so then we're going to get here a sum of m times k products 1 times 1. But 1 times 1 is equal to 1. So we're going to get m times k sum of 1s, which is exactly what we have here. Now, by definition of characteristic, n was the smallest number such that the sum of n ones is equal to 0. And so here, m and k, the factors of n, are strictly less than n. So this implies that 1 plus 1 plus 1 m times is not equal to 0. And the same is true for the sum of k ones. Right? So we have that n, by definition of characteristic, was the smallest number such that the sum of n ones is equal to 0. So smaller numbers of ones will not give us 0. And here, so what we obtain is that f has divisors of 0. So now we've found two non-zero elements of f such that their product is equal to 0. And this is a contradiction, because we know that a field cannot have divisors of 0. So it is not possible in a field to have two non-zero elements with a 0 product. So this gives us a contradiction, and the source of this contradiction was our assumption that n is composite, that we can write it as a product m times k. And so this gives us a conclusion that this assumption cannot possibly hold. And so this means that if we have a field with a finite characteristic, then this characteristic must be a prime number. So we conclude that a characteristic of a field is either 0 or it's a prime number. Now, and for finite fields, the characteristic of a finite field is not 0, but it's some prime number. So now let us prove a proposition. So let f be a field of prime characteristic p greater than 0. Then f contains zp as a subfield. So we know that zp is a field itself. And so basically what we are saying here is if we have a field of characteristic p, then it contains zp as a subfield. Now, so let's prove this. So consider the following subset in F. So we consider 0, 1, 1 plus 1, dot, dot, dot. So 1 plus 1 plus 1, p minus 1 times. So here, p was the smallest number of ones that added together will give us 0. So this tells us that all elements here are non-zero, and in fact the same argument as we used in our very first lemma shows that actually all these elements are distinct. So this gives us p elements. So this is a subset of p elements in F. And so what we see is that this subset is closed under the addition, right? So closed under addition. Because if we add some number of ones and another number of ones, then we just get more ones, right? And then if we obtain p ones, then we know that the sum of p ones is equal to 0, so we can cancel it. And then we can always reduce it to some number of ones which is smaller than 1. So in fact, what we see is that addition here works as addition mod p. But the same is true for multiplication. So here we get that in this subset, addition and multiplication work mod p. So this means that with respect to addition and multiplication, this subset is essentially ZP. But, so the only thing that we need to know is that this subset is closed under inverses, right? But what we know is that ZP is a field. And so this means that for every x in ZP, which is not 0, there exists y in ZP such that x times y is equal to 1. But then this means that y is equal to x inverse. And so this means that because we know that ZP is a field, we know that this set is closed under multiplicative inverses as well. And so what we can see here is that inside this field F, we have a subset that behaves like a field ZP. And that's what exactly we call a subfield, right? So here, what we proved is that inside F, we have a subset which is ZP. And so these are just multiples of 1. Now, what would be the analog of this proposition for fields of characteristic 0? So here, let's state a proposition. Let F be a field of characteristic 0. Then F contains Q, the field of rational numbers, as a subfield. And I leave this as an exercise. Right? So basically, the idea here is that it's not enough to take sums of ones. Well, first of all, in case of characteristic 0, because we are not going to get to 0 eventually here. So this means that we need to go to the left, so that we have to take -1, -2, and so on, right? But then this set is going to be closed under addition and multiplication, but not under taking inverses. And so if we take inverses of these elements, then we're going to get the subfield Q in any field of characteristic 0. So for example, so if we take the field of real numbers, then inside we have the field of rational numbers. And so in fact, any field of characteristic 0 must contain rational numbers inside. So far, all the finite fields that we knew were ZP. Let's construct more finite fields. So let's begin with Z3. So in this field, we have elements 0, 1, and 2. Now let's compute squares here. So we have 0 squared is equal to 0, 1 squared is equal to 1, and 2 squared, which is 4, mod 3 is equal to 1. So what we see is that in Z3, x squared is not equal to 2. So there is no x such that x squared is equal to 2, right? And so this means that there is no square root of 2 in Z3, right? So this is what we mean by writing this. Now, let's consider the following field. So let's consider a field that has elements that look like this. A plus b square root of 2, where this is treated as a symbol. So it's not 1.4 something, but just a symbol square root of 2, where a and b are elements of Z3. Right? So now on this set, we can define addition. Right? So if I have a1 plus b1 square root of 2 plus a2 plus b2 square root of 2. So this is, so we just add a1 plus a2 plus b1 plus b2 square root of 2. Right? So this is addition. And we can define multiplication. a1 plus b1 square root of 2 times a2 plus b2 square root of 2. So this is equal to a1 times a2 plus a1 b2 plus a2 b1 times square root of 2 plus b1 b2. And so our convention will be that square root of 2 squared is equal to 2. So times 2. Right? So this will define multiplication. Now, the real question here is about inverses. Can we define inverses for such elements? And so here, what we say is that 1 over a plus b square root of 2. So the trick that we're going to do is we're going to multiply numerator and denominator by reciprocal. So we'll write it as a minus b square root of 2 times a plus b square root of 2 times a minus b times square root of 2. And now this can be simplified. So here we have a minus b square root of 2 over, now by usual algebra, so this is going to be a squared minus 2b squared. And so what happens here is because in Z3 x squared cannot be equal to 2, so this means that a over b squared is not equal to 2 either, right? So because no element of Z3 squared gives us 2. And so this means that if a or b is not equal to 0, so it forces that a squared minus 2b squared is not equal to 0 in Z3. And then we can perform division. So this will be a over a squared minus 2b squared minus b, or maybe plus negative b over a squared minus 2b squared times square root of 2. And again, so this will be we can calculate in Z3, and this we can calculate in Z3. So this means that this result is going to be an element of f. And this shows that if we take a non-zero element of f, then it is going to be invertible. Now let's just do one more example here. So what is 1 over 2 plus square root of 2? Right? So here a is equal to 2, b is equal to 1. So what is a squared minus 2b squared? So 2 squared is equal to 1 minus b squared is also equal to 1. So it's 1 minus 2. And 1 minus 2 is the same as 1 plus 1. So which means that this is 2. So what we get is we get that this is going to be so a, which is 2. So it's 2 over 2 plus negative b, so it's minus 1 over 2 times square root of 2, right? So 2 over 2, this is 1, and minus 1 is equal to 2, so this is 1 plus square root of 2. And we can even check, right? So let's check that these two elements are inverses to each other. So here we need to multiply them and see that the product is equal to 1. So let's do this. So if we multiply this, then we get 2 plus, so we get root of 2 plus 2 root of 2 and plus root of 2 squared, right? So here 3 times root of 2 is equal to 0. because we are in Z3, right? So 3 is equal to 0. And so what we get is we get 2 plus 2, which is equal to 1 in Z3. So indeed, as we expected, these two elements are inverses of each other. And so this argument shows that, in fact, so this set of elements is closed under addition, multiplication, and also we have inverses of non-zero elements. So this means that this is a field. Now, the question, so how many elements are in this field? Right? So we have 3 possibilities for A and 3 possibilities for B. And we take various combinations of this. So we take various pairs. So this means that the number of all possible combinations of such pairs is 3 times 3. So which is 9. And so what we have here is we have a field with 9 elements. Now, what is the characteristic of this field? Right? So in this field, we have Z3 that sits inside. Right? So if we just set B to be 0, then we obtain Z3. And we still have 1 plus 1 plus 1 will be 0 in F. And so this means that the characteristic of this field is equal to 3. So what we obtain here is we obtain a field with 9 elements of characteristic 3, and we see that we have Z3 sitting inside as a subfield, so in agreement with what we have proved. Now, let us generalize this construction. Suppose remainder M in ZP has a property that x squared is not equal to m for all x in ZP. So then we can take F to be the following set. We can take A plus B square root of m, where this is treated as a formal symbol, where A and B are elements of ZP. And in the same way as we did here, one can show that F is a field. So the number of elements in this field is going to be, well, we just take pairs of A and B, where A and B have P possibilities for their values. So this means that the total number of possibilities is P times P. So this means that here we get a field with P squared elements. And so what we have is that the characteristic of F is going to be P. Because in this field, if we add P times 1 with itself, so we are going to get 0. And ZP will be a subfield sitting inside F. How do we know that we can find such an M, such that no square is equal to M? Well, so what we can observe is that we always have that minus x squared is equal to x squared. And so this means that we will have pairs of different remainders that will have the same square. And this tells us that the number of squares in ZP is smaller than the number of elements in ZP. And, well, the only exception is, so P is equal to 2, right? So this will not work for P equals 2. But if P is not equal to 2, right? So if P is different from 2, then there exists an M in ZP such that M is not equal to square of any element, right? So for Z3, this is an element 2. Now let us start building bridges with linear algebra. We have a proposition. let F be a field with a subfield K. Then F is a vector space over K. Now, so what we have here is we have here two fields. One field sits inside a bigger field. And so this whole proposition is just a matter of point of view. So F is a field. So here we can add elements of this field and multiply elements of this field. What we're going to do is we're going to change our perspective. We're going to think of elements of the field F as vectors and elements of the smaller field K as constants or scalars. And then addition of vectors of elements of F, we interpret this as addition of vectors. And so now we're going to forget that these vectors can be multiplied. But we only can remember that we can multiply elements of F by elements of K, which is a subset of F, right? And so this will be the operation of multiplication of a vector by a scalar. And then it just amounts, so we need to verify that all axioms of a vector space hold here. And it turns out that these axioms of a vector space will simply follow from the axioms of a field. So the axiom of a field are just stronger than axioms of a vector space. And so then what we obtain is that in this situation, F can be viewed as a vector space over the field K. So as a corollary, we can state the following. So let F be a finite field of characteristic P greater than 0. Then F is a finite dimensional vector space over ZP, right? So we proved that if we have a finite field of characteristic P, then we have ZP as a subfield. And by this observation, so this makes a finite field be a vector space over ZP. So we just treat elements of a finite field as vectors and elements of ZP as scalars. And so we get a vector space structure. And this vector space is finite dimensional. So let's recall what's the definition of a finite dimensional space. A space is finite dimensional if it is spanned by a finite number of vectors. But F is a finite field. There is only a finite number of vectors in it at all. So this means that automatically, since it's finite, then it certainly is finite dimensional. And so then we get that F is a finite dimensional vector space over the field ZP. And we already know something about finite dimensional vector spaces. In particular, we know that any finite dimensional vector space has a basis and a dimension. So let's explore these ideas. So suppose dimension of F over ZP is equal to n, right? So if it's a finite dimensional vector space, then it has a finite dimension. And let U1 through UN be a basis of F as a vector space over ZP. So what does it mean? So this means that any element, so for any element v in F, there exist scalars a1 through an. And so these are elements of Zp, because we are considering this as a vector space over Zp, such that V can be written as a linear combination a1 u1 plus an times un. So this tells us that any vector or any element of F can be written in this way. And moreover, we claim that this way of writing V is unique, right? So this is unique way of expressing. Let's see what happens if we have two ways of expressing the same element in this form. So suppose we have this element, which is equal to b1 u1 plus bn un. So if we subtract, if we move everything to one side, then this will tell us that a1 minus b1 times u1 plus an minus bn times un is equal to 0. But this is a basis here over Zp. So this means that these elements are linearly independent. And what we have here is a linear combination of these elements with coefficients in Zp, which is equal to 0. So by linear independence, each coefficients here must be 0. So this means that a1 must be equal to b1, a2 must be equal to b2, and an must be equal to bn. So this tells us that, well, two things, that every element of a field can be written as this linear combination, and moreover, this can be done only in one way, right? So we cannot have two different linear combinations representing the same element. This allows us to count how many elements in F do we have. The number of elements in F is equal to the number of all possible linear combinations of this form, so with a fixed basis. And so these linear combinations are determined by our coefficients a1, a2, an. Each of these comes from Zp. So we have p possible values for a1, p possible values for a2, and p possible values for an. Then to count the number of combinations, we need to multiply our number of choices for the first term, number of choices for the second term, and what we get is p times p times p, and this is n times. And so what we get is p to the power n, where n, so what's the meaning of n? N is the dimension of F as a vector space over Zp. And now we prove the following theorem. That so a finite field F of characteristic P has P to the power n elements, where n is the dimension of F over the field, its subfield of Zp. This agrees with our construction of this field a plus b square root of m, right? So where a and b are in Zp. Now, so we said that the size of this field is p squared. Now, what is the basis of F over Zp? Right. So what we see is that the way how we wrote these elements can be interpreted in the following way. So these are a times 1 plus b times square root of m. So this means that the basis over zp for this field is 2 elements, 1 and square root of m. And because the basis has 2 elements, so this also means that dimension of f over zp is equal to 2. So this is a 2-dimensional vector space over zp. And so it has p squared elements. And here we see the basis of this field over zp. We know that the field of rational numbers is a subfield in the field of real numbers. So this tells us that the field of real numbers can be viewed as a vector space over the field of rational numbers. So now this raises a question. Is R finite dimensional? As a vector space over Q? Well, if it is, then there would be a basis of real numbers as a vector space over Q. And so we would like to know what that basis might be. In order to answer this question, we need to dive a little bit into number theory. And we'll start with the lemma that says that square root of 2, which is a real number, is not a rational number. So this means that square root of 2 cannot be written as m over n, where m and n are natural numbers. Let's prove this lemma. And we prove this lemma by contradiction. So suppose we can find natural numbers m and n such that square root of 2 is m over n. So we know one fact about fractions, that fractions may be reduced. So this means that if m and n have common factors, then these common factors can be cancelled. So we assume that this fraction is reduced. So that is no common factors. So this means that only one of these two numbers may be even. So only one of m and n may be even. Or perhaps neither, but not both. So we assume that it's not the case that both m and n are even, because in reduced fractions this cannot happen. So then let us square both sides. So we get square root of 2 squared is equal to m squared over n squared, which implies that m squared is equal to 2n squared. So here we just multiply by n squared. Now, what does it mean? So this implies that m squared is even. And we know that the square of an even number is even, and the square of an odd number is odd. So this means that m cannot be odd. So this tells us that m is even. And we can write m as 2 times k. So now let's substitute this into this equality. So from here we get that 2 times k squared is equal to 2n squared. So this is 4k squared is equal to 2n squared. And then this tells us that 2k squared is equal to n squared. But then this tells us that n squared is even. And this tells us by the same argument that n is even. And this is a contradiction, because our assumption here was that for a reduced fraction we cannot have both m and n even. And this is what we've got here. We got that m is even and n is even. So we get a contradiction. So this means that square root of 2 cannot be written as a reduced fraction. And so this means that square root of 2 cannot be written as a fraction at all. This fact, so this lemma, was discovered by mathematicians in ancient Greece in Pythagorean school. And this caused a big shock for them, because at the time there was no concept of a real number. And the understanding was that all numbers are rational. And there was this big quest to find a rational number representation of a pi, right? So can we write pi as m over n, right, as a rational number? So today we know that this is not possible, but at the time of ancient world, so all numbers were treated as rational numbers. And so this proof that square root of 2 cannot be represented as a rational number was really shocking, because certainly it was clear that square root of 2 exists, right? So if we just take a square with side 1, then by Pythagoras' theorem, its diagonal is square root of 2. So this means that this number as a length of an interval certainly exists, but it cannot be represented as a number, as understood at that time. And so this was like a break of a paradigm. So this means that, so this was telling people that there are numbers beyond rational numbers. But there was no understanding, conceptual understanding, how to treat such numbers, because, well, at the time there was no concept of a decimal point. And so these decimal expressions of numbers did not exist. And so this was such a big shock for Pythagoreans. So what they did is they just made this research classified. So they kept this a secret, and so that they could continue teaching mathematics at schools. And this was a rather dramatic turn of events. Now, how can we interpret this lemma from the point of view of vector spaces? So as a corollary, we can say the following, that the following set, 1 and square root of 2, so this set is linearly independent over Q. Now, so let's recall, so when two vectors are linearly independent, so if we have V1 and V2, so this set is linearly independent if and only if V1 and V2 are not proportional. So this means that neither is a constant multiple of the other, right? But when we say constant multiple, so we mean that it's constant multiple over Q. So this means that it's not a rational constant multiple. And so in particular, so if square root of 2 was a multiple of 1, so this would tell us that, so well, square root of 2 is not a multiple of 1. So it's not m over n times 1, right? And so this is an element of Q, right? So since we know that square root of 2 is not a rational number, so this also tells us that square root of 2 is not a rational multiple of 1. And by inverting this, so this tells us that, so this is equivalent to saying that 1 is not n over m times square root of 2. So this means that neither square root of 2 is a constant multiple or rational multiple of 1, nor 1 is a rational multiple of a square root of 2. And this tells us that this set is, so it's a subset in the set of real numbers, and this set is linearly independent over Q. We can ask a question. Is the following set 1, square root of 2, and square root of 3 linearly dependent or independent over Q? So in other words, can we find a rational linear combination of these three numbers with non-zero coefficients that is equal to 0? So there is one lemma that we proved in the previous lecture that says the following, that suppose the set V1 through Vk is linearly independent. Then the set V1 ... Vk and U is linearly dependent if and only if U belongs to the span of V1 Vk, right? So, or we can say that this is linearly independent if and only if U does not belong to the span of these vectors. And so this lemma that we proved in the previous lecture is applicable to this situation. Here we have a linearly independent set, 1 and square root of 2. And now we're enlarging it. And we want to understand linear independence of this. And then, so this result tells us that this question is equivalent to the question, is it true that square root of 3 belongs to the span or rational span of 1 and square root of 2? We come to the question, so is it true that square root of 3 belongs to the span, and here just to make it clear we'll say span over Q, of 1 and square root of 2. So what does it mean? So this means that we can write square root of 3 as a times 1 plus b times square root of 2, where a and b are rational numbers. So the question is, can we do this? All right, so let's assume that this is possible, and let's square both sides. So then this would imply that 3 is equal to a plus b square root of 2 squared, so which is a squared plus 2ab square root of 2 plus b squared times square root of 2 squared, right? Or, so this also tells us that 2ab times square root of 2 is equal to 3 minus a squared minus 2b squared. Let's assume that a and b are non-zero. So then this tells us that square root of 2 is equal to 3 minus a squared minus 2b squared over 2ab. And we see that the right-hand side is a rational number. And so that's a contradiction, because we know that square root of 2 is not a rational number. If one of these is equal to 0, so if b is equal to 0, so then this would tell that square root of 3 is equal to a, which is a rational number, right? So, but this is not true. Like we proved the lemma that square root of 2 is not a rational number. In the same way, we can prove that square root of 3 is not a rational number, right? And if we assume that a is equal to 0, then we will get that square root of 3 is equal to b times square root of 2. And then this would mean that square root of 3/2 is equal to b, which is a rational number. And again, this is a contradiction. So exactly how we proved our lemma about square root of 2, we can also make a proof that square root of 3 is not a rational number, and the square root of 3/2 is not a rational number, right? So square root of 2, square root of 3, and square root of 3/2 are all not rational numbers. So the proof is easily modifiable to cover these cases. And so this tells us that no matter what is the situation with a and b, we come to a contradiction. And so this means that square root of 3 cannot be written as a rational linear combination of 1 and square root of 2. And so then we get that square root of 3 does not belong to the rational span of 1 and square root of 2. And so the conclusion is that this set 1 square root of 2 and square root of 3 is linearly independent over Q. And now let me state a problem for you. So it's somewhat challenging, so I'll put a star here, right? So that the set 1 square root of 2, square root of 3, square root of 5, square root of 7, and then we just go over all square root of 11, just square roots of prime numbers. And we just form an infinite set like this, is linearly independent over Q. Right, and so the conclusion from this exercise is that R is infinite dimensional as a vector space over Q. Now, indeed, so if we have a finite dimensional vector space, then we can take its dimension. And then we know that if we take more vectors in our vector space than its dimension, then this set will be linearly dependent. And here, the existence of an infinite linearly independent subset would mean that this vector space cannot be finite dimensional. So if we can prove that there is an infinite linearly independent set of vectors in our vector space, this proves that this vector space is infinite dimensional. The idea of proving that R is infinite dimensional over Q is by constructing explicit infinite linearly independent set. So there is an alternative approach to this claim, which is based on counting. So let's give a definition. So an infinite set S is called countable if we can list all elements of S in a sequence. So let's give some examples. So for example, we take the set Z of integers, so which are positive and negative. So here we can exhaust elements of Z in the following sequence. We can take 0, 1, -1, 2, -2, 3, -3, and so on. So now we get one sequence, and this sequence will contain all elements of Z. So this tells us that Z is countable. Let us just recall notation. So A cross B for two sets A and B. So this is the set of pairs AB, where A belongs to the set A and B belongs to the set B. Right? So this is what is called Cartesian product of two sets. So this is the set of pairs. So we can prove the following lemma. So if A and B are countable, then the Cartesian product A cross B is also countable. So let's give the sketch of a proof. So if the set A is countable, then we can kind of arrange it in a sequence. A1, A2, A3, and so on. So if the set B is countable, then we can have a sequence exhausting all elements of this set. So geometrically, then we can think of the Cartesian product as dots on this plane, right? So this dot will be a pair A1, B1. This is the pair A2, B1. And this is the pair A1, B2. And so on. So what this lemma claims is that the number of these dots on the plane is countable. And indeed, we can arrange them in a sequence. So if we do this sort of walk on this plane. Right, so if we just walk along pairs in this way, then we can list them all pairs of this element of the Cartesian product in one sequence. And this means that this Cartesian product of two countable sets is countable. So as an example, what we get is the set Z cross N is countable. Right, so because Z is a countable set, the set of integers, as we have seen here, and the set of natural numbers is clearly countable because it's 1, 2, 3, 4, 5, and so on. And now let us look at Q. What is Q? Q is the set of fractions m over n, where m belongs to z and n belongs to natural numbers. Right? And so what we see, so since we can arrange the set of pairs of z cross n in one sequence, so this tells us that we also can arrange all rational numbers as one sequence. Well, there is a little bit of a problem here of duplication, that the same rational numbers can be written as two different fractions. But what we can do is we can arrange them all with duplications in one sequence and then throw out from this sequence all duplicates. And so then So what we get is that Q, the set Q, is countable. So we can, using these ideas, we can arrange all rational numbers as one sequence. Since the set of rational numbers is countable, applying this lemma, so what we get is the set of pairs, or Cartesian product of Q with itself, is also a countable set. Now, so let V be a two-dimensional vector space over Q. So we can choose a basis. So we know that any finite dimensional vector space has a basis. So choose a basis of V. So we have a set V1, V2. Then for every vector U in V, we can write, so there exist A and B in Q, so that U can be written as A times V1 plus B times V2. So this means that vectors in our vector space V are exhausted by pairs. Right? So if I have a pair of numbers A and B in Q cross Q, then any such pair gives us a vector U in V. And moreover, in this way, we exhaust all vectors in V. But here we saw that Q cross Q, so the Cartesian product or the set of all pairs of rational numbers, is countable. So this tells us that, so this implies that V is countable as a set, because elements of this vector space can be indexed by pairs, well, by two rational numbers. And we know that the number of pairs of rational numbers is countable. So what we get is that a two-dimensional vector space over Q is countable. So now we can generalize this, right? So since we know that Q cross Q is countable, then Q cross Q cross Q will also be countable if we apply this lemma again. And so this means that the set Q cross Q cross Q n times is countable. So by repeated application of this lemma. And as a conclusion of this, we get the following fact, that if V is an n-dimensional vector space over Q, this implies that V is a countable set. So in other words, any finite dimensional vector space over Q is a countable set. So we can state the following theorem, that the set R of real numbers is not countable. So this means that the set of real numbers cannot be arranged in one sequence. And as a corollary to this, we get a different approach to the question of dimension of R over Q. As a corollary, we get that R is infinite dimensional as a vector space over Q. Right? So because here we prove that any finite dimensional vector space over Q is countable. And if R is not countable, this means that, and we know that R is a vector space over Q, this tells us that R is an infinite dimensional vector space over Q. Now let's give a proof of this theorem. And so this method of proof is called Cantor's diagonal. So we are going to prove by contradiction. So let's assume that we can arrange all real numbers in a sequence, in one sequence. x1, x2, x3, and so on. So let us consider their decimal expansions. So for example, say x1 is equal to 3.141 ... x2 is minus 2.71 ... x3 is 0.1111 ... right? So we consider this sequence that supposedly lists all real numbers, and we look at their decimal expansion. So now we're going to construct a new real number. So construct a real number y, which will be equal to 0 point something ... in the following way. So choose its first digit. So choose its first digit after decimal point. In any way which is different from the first digit after decimal point of x1. Then it's, so for example, so here, so x1 has the first digit of 1, and I will choose the first decimal digit of 2. Then its second decimal digit after decimal point, we choose something that's different from the second decimal digit after decimal point of x2, right? So here it's 7. I'm going to choose 3, right? And the third digit after decimal point, just pick anything which is different from the third decimal digit of x3. So x3 has the third digit of 1, and I will choose 7, and so on. All right, so there is a lot of flexibility of constructing that real number, but taking this sequence, infinite sequence, that supposedly lists all real numbers, so we can construct a new real number, so which is different from x1 in the first digit after decimal point, from x2 in the second digit after decimal point, and so on. And what we see is that y is not in this sequence. So this means that y cannot be equal to xk, because kth decimal digits of y and xk are different by our construction. And this gives us a contradiction, because we assumed that all real numbers are listed in one sequence, and we constructed a decimal expansion So that is a new real number which is explicitly not in this sequence. So we're just doing this diagonal in the decimal expansions, right? And so this is the reason why this is called Cantor's diagonal. And so in this way, we prove that the set of real numbers is not countable. So it's not possible to list all real numbers in one sequence. And so then we get our conclusion that the set of real numbers is an infinite dimensional vector space over its subfield Q, rational numbers.